we are going to talk about free body diagrams and writing net force equations. So this is something that's super important, especially in the next unit. But this unit, we're going to make sure you have the basics. So a free body diagram is just a drawing that you do that contains every force that is acting on a particular object. So if you have something as simple as a box sitting on a table, you have gravity that is going to be pulling straight down on the box. So we're going to label that with Fg for force of gravity. You also have the the table pushing up on the box. And that is a surface that it's pushing against and the surface is pushing back. So that's going to be a normal force. And so that's Fn. And if the box isn't moving, it's just going to sit like that. And that's going to be your whole diagram. So a force equation basically takes the forces that you have on the diagram and it makes an equation to describe the net force acting on the object. So in this case, we have normal force and gravity. Now, because these are both vectors, our equation does need to include the direction the forces are pointing. And so we're going to use traditional like up and right are positive, down and left are negative kind of signs. So to write a force equation, these are in the y direction. So we can write one in the x direction and in the y direction. In this case, we don't have any x forces, so we just have a y force. So this symbol means net. So net force is the same as total. So net or total. But if you see me ask for a net force equation, and it's in the y direction, so I put the y. So you start by writing anything that's acting in the positive direction. So in this case, that would be your normal force. So Fn. And then anything acting in the negative direction. And you're going to go minus because it's negative. Fg. And that's it for this one. And net force equals ma. That's Newton's second law. And so that's always going to equal ma. And this is the y direction. So we're going to put y. So it's the acceleration in the y direction. So sometimes you're going to have acceleration in both x and y. And so we need to keep that straight. So it can be as simple as that. It can be more complicated. So let's go to a slightly more complicated option. So let's say you have the box on the table. And now I'm going to push it sideways and make it start sliding across the table. So in that case, we know we still have gravity pulling down. And we still have normal force pushing up from the table, okay? But if I'm pushing this way, that gives us an extra force, so let's call that Fp, okay? And then if I'm pushing to the right, the friction between the box and the table is going to push back to the left. Okay? So in this case, the net force in the y direction is going to be the same as the last one, because again, it's the same box sitting on the table. And then I am just going to start pushing on it. And this is what would happen next. So I'm pushing it sideways, friction's pushing back. So now we're going to look at what the net force in the x direction would look like. And so anything in the positive direction is going to go first, and with a positive. So the Fp is positive. So Fp. And then the friction is going against it, so it's going to be negative. So minus Ff equals ma in the x direction. So this one has two equations to describe its motion. Both of these apply. One is in the x direction and one is in the y direction. Okay? Now it can get a little more complicated again. So next step is, what if one of them is at an angle? So let's say I'm pulling with a string at an angle. We still have gravity pulling down. We still have the table pushing back up, as long as I don't pull too hard. Friction is still going to push this way because it's going to go opposite the normal force. The friction and the normal force are going to be at right angles all the time. Okay, so then this I'm going to call FP. It's at an angle now. So we don't know what this angle is, we just know it's at some angle. Okay, so this is going to be like our two-dimensional motion. So if you have something acting at an angle, you need to include that in both the x and the y, but the full amount is not going to be in either direction. So like FP by itself is not going to occur in either equation, but I am going to have FPX and FPY. So this is going to be another one of the vectors that I'm going to use sine and cosine to solve and make the triangle into x and y parts. So we're going to start over because it's going to be a little different than the last one. Okay, so I can do x or y first, it doesn't matter. I typically start with x just because, no reason, I just tend to do it for consistency. So we are going to do the x first. So when you do this, you need to remember that the FP is not totally in the x direction, only part of it is. And so we're going to write FPX so that we know it's only this component that's pulling in the x direction. And then we also have the friction. Oh, I labeled that wrong. It's not normal force, it's friction force. Friction force. Friction force is going backwards. So that's going to be a negative. That's going to equal MAX. Okay, another way you can write this, some people like to start with this. Some people will skip straight to doing a sine or cosine. So this is acceptable. Another acceptable answer would be to do this as actually doing the x component. And so x we see is the one touching the angle, so that's going to be your one that uses cosine. Instead of writing FPX, you can just write FP cosine theta, because that is the x part of that triangle, minus FF equals MAX. So it doesn't really matter whether you start with this or this, as long as you make sure you do your sine and cosine right. So these would both be acceptable answers to this question. So those would be examples of my x equation, and then I'm going to do the y equation also. So this is up and down. Now I have two forces in the positive direction, and I have one force in the negative direction. So I'm going to start with the easy one, and that's my Fn. Okay, and then I have FP partially pulling up, but not the whole thing. So I'm going to do just the y component. So FPY, and then the FG is still pulling down, so it's going to be negative FG equals MA in the y direction. Now again, just like up here, if you'd rather, instead of writing FPY, if you'd rather go ahead and put your sine and cosine in, you could write this as Fn plus Fp, and then the y is the opposite one, it's this one here. So that's your opposite, so it's going to be sine so you could write it like that. So x would be one of these two, y would be one of these two. Both of those are acceptable way to write that. We're going to do a lot more with these later, but for now I just want to make sure everybody knows how to write the initial equation. That is pretty much the big idea. I do want to point out something. So if I look at these two sets of equations, I see normal force in both of them. If this is the same block or same box that is just sitting still, or that I'm pulling here with a string, we know FG is going to be the same because that only depends on the mass of the box and the fact that we're on Earth. This thing that is super important is that the normal force may not be the same in both situations. So in this case, it's just sitting still. So your normal force and your gravity are going to cancel out. They're equal amounts in opposite directions, and so they're going to end up canceling out. So your Fn and your Fg are going to be the same. In this case, I have gravity pulling down. My pull in my rope, or whatever it is going to be pulling up, and normal force is going to make up the difference. So normal force is essentially going to be whatever part of the weight is not being supported by the rope. So like, let's just make up some numbers. Let's say FG was 15 newtons, just to make these numbers easy. And let's say FPY was 8 newtons. What that means is gravity is pulling down the 15. The rope is supporting 8 of that. The normal would be taking the rest. So if this is supporting 8 newtons, if this part of the triangle is 8 newtons, that means this would be the rest of the 15, which would be 7 newtons. So it may be the same box, still sitting flat on the table. This one's sliding sideways, but here the normal force has to be the full 15 newtons. Here it's only going to be the 7. So normal force is a little tricky because it depends on what you're doing. The same table can provide anything up to its breaking point. So if you have something that's just barely touching the table may be pushing up with 0.5 newtons. If you have a person sitting on the table, it may be pushing up with 900 newtons. The table can do anything. It's basically just going to push back with whatever force you're pushing on it. So like in this case, if gravity is pulling down, but the rope is taking some of that weight, this just has to take the rest. So these two added together are going to equal that. So we're going to do some more later after this first test on like how we're going to use this and how we're going to apply it. Right now we're just focusing on that you can find all of the different pieces. And so really that's going to come down to, can you do Newton's second law as a problem? Let's get that to its middle more. So can you do F equals ma? Can you do, why did I just blank? Fg equals mg? And can you do friction force, which we're going to be working on next time, which is this. So these are kind of like the 3 big ideas we're going to focus on right now, along with the drawing the diagrams and the writing the force equations. So we're going to focus on this piece of it. Couple notes. Remember, this mass is going to need to be in kilograms. If you're given something in grams, you have to convert the unit. Same thing here. The mass has got to be in kilograms. Remember, this is your 9.8. Now we're not going to do negative 9.8 because remember up here where we did the minus? This is where the negative is going to come in. So we are just going to plug in 9.8 for little g. The negative will come in our equation that we're writing from our free body diagram. And then we'll talk about friction later, but it's essentially based on the normal force and then this coefficient of friction that we'll talk about later. So that is it.